okay, so I've got all this nice ciphertext on disk. What about when all my clear text is in the machine and someone gets access to dev KMM because they've got all privilege? Well, it's all bets are off. When you've got control of the full machine, all bets really are off if you've got all privilege on it. Because at the end of the day, if the data was ever decrypted, chances are the key is still lying around in memory somewhere. But there's functionality in ZFS to help reduce the risk. Independent of ZFS Crypto, and these features are there just now, you can actually control on a per data set basis whether or not you cache the blocks. You can cache nothing, cache just ZFS as metadata, or you can cache everything. And this applies to the DRAM in memory cache and also what would normally be on an SSD, which is called the level 2 ARC. So the level 2 ARC in ZFS is always encrypted because it's persistent storage. Even though we don't treat it in ZFS as if it is actually persistent. So we have to encrypt it there. So when secondary cache says all, it actually really means encrypted. But primary cache in DRAM, well, that's where your clear text is. Your question? Do you mean DRAM or do you mean virtual memory? Right, so you can, with ZFS, remember I mentioned the ZVols at the beginning, these things that look like disks or just carved off piece of your storage. We can swap on those. So if you have your swap ZVol tagged as being encrypted, where the key comes from dev random, you have encrypted virtual memory for when those pieces of virtual memory are paged out onto disk. We do not at this point, and have no plans to do, encryption of the stuff in DRAM itself. Mainly because it would be quite a fundamental change to how ZFS manages its cache. It's possible, and in fact, the more interesting case is probably to have compressed data in memory for when you get to the case where the compression algorithm, we've got plenty of CPU, but we're running out of DRAM. That might be a good trade-off that some people want to make. Encrypting the data in DRAM, what is it actually going to buy you? It depends. Are you concerned about some of your DRAMs accessible, but the keys aren't? If you're going to encrypt it, where do you put the key that you encrypt it with? Maybe the key for encrypting this is actually in some sort of secured storage. Not a TPM, because TPMs are too slow to do the encryption themselves. They'll only help you with a wrapping key. So it's hard to find the use case for encrypting everything in memory, but certainly encrypting things like the secondary cache, which ends up on persistent storage, certainly encrypting any virtual memory pages that are swapped out to disk, which is really what I'm saying here. So in ZFS, we have the concept of a hybrid storage pool. And usually, the hybrid storage pool in ZFS is spinning Rust disks that we all know and love, anything from 4200 RPM up to 15K RPM in an enterprise class drive, augmented with nice, fast, solid-state drives. And ZFS uses solid-state drives for two different reasons. It uses solid-state disk drives that are very fast to write to for what's called its intent log, the separate log device. Any data going there has to be encrypted because that's persistent storage that we have to read after a reboot. The intent log is what we use to provide POSIX semantics for when a POSIX app says, open this file synchronously, or it explicitly does an fsync, that must not return until that data is on stable storage. Some file systems, in particular some operating systems, NFS clients, do not properly implement that in their default configuration. They will tell you it's on stable storage, but it's not really. In ZFS, we always, and this is where it goes back to when I said earlier, we assume the disk does not lie to you. If the disk says it's on stable storage, it's hard for us to argue with the disk, but some of them, it's not really on stable storage, it might be, or some of them deliberately lie for performance and some of them are just buggy. The other case where ZFS uses solid-state drives is for the level 2 ARC, and this is a cache. And the idea with the level 2 ARC is that you can use slower, cheaper, less power-consuming 7200 RPM or maybe even 5400 RPM disks to store your data, and trade that off with having a large amount of DRAM and a large amount of reasonable amount of SSD that's very fast to read from. These SSDs are persistent, and these are what make up the level 2 ARC. So what happens is that when something is going to be evicted from DRAM and it's getting written out to level 2 ARC, if it's for an encrypted data set, it gets encrypted. Now, it gets encrypted today with an ephemeral key because the way that ZFS deals with the level 2 ARC is it completely ignores it on reboot, and you have to warm up the cache again. So we may as well just use an ephemeral key. That will change in the future, and when it does, that part of ZFS encryption will change along with it. So why not just do full disk encryption? Some of the disk drive manufacturers, particularly the big common names, are putting encryption straight into the drive. It's almost 100% transparent to the user. Chances are you only need to enter one thing once for a disk, and that's it. Near zero performance impact because it's all below the drive. It's in the drive firmware. And in fact, I heard from some of them at an IEEE conference last year that very soon they'll be in a situation where all their drives are actually crypto compatible, and it's a 1-bit flip on their firmware. They'll charge you for that bit being flipped initially, but as far as they're concerned, it'll be one piece of firmware. So why bother? Well, what's the disadvantages of full disk encryption? Many of these full disk encryption solutions, you can't get access to the ciphertext. So how do you know it's really encrypted? You've got to believe that drive. You've got to believe that drive manufacturer did it all right. Okay, so let's assume you do trust them and take that one off the table. So all of the current versions encrypt all the data on these drives, which, by the way, are 2 terabyte and above drives, all encrypted with the same encryption key. That is beyond NIST guidelines already. It's all encrypted with the same algorithm, the same mode, the same key length. And you can't change the encryption algorithm. So what happens if something is wrong with AES or a particular mode that they've chosen? What's your choice? Well, you've got to buy a new disk, and I've got to throw away the old one. But now I'm back to the problem of, depending on how the algorithm was broken, I might have to be back to throwing away the disk by destroying it. I can't reuse it. So software solutions are more flexible here. And in particular, for the key management, because in ZFS, the key management is at the file system level, not in the disk drive, and in fact, the drives are below your RAID level. So it's not a shim between the real drive platters and the file system. It's not a shim at the RAID level. You don't have complex key management down at the disk level. And also, ZFS hybrid storage pool, there is no enterprise class SSD on the market that does encryption. There are consumer level USB thumb drives, but those just don't perform well in the enterprise. So there is no SSD on the market today that you can use in a ZFS hybrid storage pool that will encrypt your data. So it's a non-starter. So we can get rid of all these problems with ZFS Crypto. Single or multi-disk pool, doesn't matter how many drives we've got, doesn't matter how many data sets we've got. They can be one wrapping key, they can be a separate one for each one. It can be separate encryption, algorithm, key length, and it allows us to ensure that we can comply with the NIST guidelines on how long we use a key, how much data we encrypt with it, and it works nicely with any enterprise class SSD. So you can keep up with the performance curve without having to worry about whether or not that SSD can encrypt your data as well. We also get encrypted snapshots and clones, which true you would get if you were using full drive encryption as well. And compression and deduplication, which just integrated into ZFS this week, will actually work together rather than against each other. And it will use the host operating systems, cryptographic acceleration, and key management if they're available. Full drive encryption certainly doesn't need the host operating system's encryption capability, but it may be difficult to integrate it into an existing key store, such as a TPM, or may be difficult to integrate it into your key management system, particularly on operating systems other than things designed for consumer devices, which is where most of these encrypting drives are targeted at this time. So what's the disadvantages of ZFS Crypto? There is still some clear text on disk. The ZFS metadata, the data about the layout of the RAID system, where the actual blocks are, so the connections between the blocks are in the clear. But all of the user data, all of the file system metadata, so the ACLs, who owns the file, whether they be Unix user IDs or Windows SIDs, because ZFS stores both, that's all encrypted. So your file names, all the user-generated content is encrypted. The dataset names are in the clear, though, because that's ZFS metadata. And I say that it's not ideal for USB thumb drives, mainly for the reason that most USB drives, people tend to put a fat file system on them. It works, providing your thumb drive is greater than 64 megabyte, which almost everyone is these days. But wait, ZFS can actually provide full disk encryption as well. Because if you're actually exporting ZFS volume over iSCSI, as far as the client machine is concerned, this is full disk encryption. And in particular, this will be the type of model that you'll get in the Sun storage appliances or anything you build as an open storage system yourself. Same for NFS and CIFS clients. The share is encrypted, and the clients don't get involved in the key management. Obviously, in all of these cases, you have to provide some layer of transport protection between the storage server and the storage client. In the case of iSCSI, highly recommend you deploying IPsec. If you're not, you don't value your data enough. And in the case of NFS and CIFS, make sure it's protected with Kerberos. At this point, there's no connection and no integration between the Kerberos keying authentication for NFS and the ZFS keys, but it's something we intend to have a look at. It's quite a hard problem to solve.
Did you say it was or was not?
It's a hard problem to solve. There are a bunch of use cases for the slides as well, if you want to read them later. And it is an open Solaris project, and the code is all under the CDDL. It should be relatively easy to port this to the other platforms that have ZFS, FreeBSD, NetBSD, and even the Fuse port to Linux, or the native port to Linux, if that continues to get traction. Because by and large, the only part of this that's specific to Solaris is the 1 or 2 calls where we say crypto encrypt. You'd change that to be whatever the Linux or BSD call is. The vast majority of the many lines of code in this project are agnostic to the actual platform. So I showed how easy it was to find a clear text. Let's create another pool. So now I've created another pool called tank. And this time I'm going to create an encrypted file system. That is the simplest case. Just say encryption on. And on here means do AES in 128-bit key length in CCM mode, because that's the one that performs best, and based on current literature is probably the best bet from a security point of view as well. So put in a passphrase.
You've said that now twice.
Yes.
The difference between 128 and 256.
Yes. There is current research that's been published in the last couple of months that indicates that AES 256 may actually turn out to be weaker than 128 because of the way it does the key schedules and the number of rounds. If you just Google for it, you should be able to find the research. The papers are pretty heavy on maths, but if you read just the abstract and the conclusion, that's basically what it comes to. The world has not fallen for AES, but it's just that 256 may not be as strong as it was originally thought to be. But it's more expensive. So AES 128 is considered by most cryptographers good enough for most people's data, and we give you the choice. If you want to encrypt with AES 256 or 192, burn those CPU cycles.
The only reason I asked the question about whether or not it really is that much more expensive is in fooling around with Kerberos NFS.
Yep.
We weren't able to measure the difference in speed between 128 and 256.
In many cases, you won't. And particularly, it depends on what kind of hardware crypto acceleration you've got. If it's on an UltraSpark T2 processor, or even on a fairly recent Intel processor or something.
It was actually
yep.
V240, which is an UltraSpark 3.
Wow, even on a V240. Wow, that's...
And, you know, it still wasn't
Yep.
appreciably measurable.
And in particular, when you're talking about something like Kerberized NFS, chances are your networking is more of your problem, or maybe even your back end into the storage. And some of the testing I've done with ZFS Crypto, because usually the first thing people ask if they're not a cryptographer is, what's the performance impact? Well, I'm going to give the normal ZFS answer. It depends on your workload. It depends on your rate of ingestion of new data and the rate of the read of new data, whether or not it's going to be a problem. So using the file benchmarking suite, I did some comparisons to see, well, what's it like to the default case in AES 128? What's it like in AES 256? And for some cases, you know, simulated OLTP, I can tell the difference between 128 and 256 in the stats, and it's noticeable. In other cases, compression is actually more of a CPU overhead than the encryption is. Yeah. You turn on gzip 9, that's your biggest problem. You can forget whether or not you're doing AES at all. gzip 9 is just going to burn all your CPU and all your memory. So it depends on your data and depends on what other things you're doing with ZFS, how much you will notice the encryption. Good question? Yeah, that's... The changes that were done to help compression help the encryption as well, in the way that things happen in ZFS pipeline. So those changes for compression are already in, and those help encryption too. The other thing that helps for encryption is because you're using, we call into the Solaris crypto framework, if you do have a hardware accelerator, we will be using task queues to go and contact that hardware accelerator and taking load off, particularly on something like an UltraSpark T2. You'll actually be taking a load off of the CPU because you go into a different part of the core. So it depends on what hardware you've got. It'll be a different problem on Intel NI. And I'm getting told time. Yep, so we created an encrypted file system. And let's just do the CP again. This time we copy it into tankfs. And if I run strings on, where was it, var temp demo d2, we're still going to see some things that strings thinks are ASCII, but these are just random things that are written on the disk. Remember I said the ZFS metadata is still in the clear? So there's still some clear text here. But these are, we don't have the text to Hamlet popping up in here. Those are just random garbage that the way ZFS writes it out. And strings is a bit simple sometimes at what really is a string. Nah. Yeah, I'm sure Shakespeare really didn't write Hamlet like that. Or maybe he did. Maybe that was the Thousand Monkeys version. So it's actually that easy to use. Now, if I go and create another file system below tankfs, then I don't get prompted to do anything because it's just inherited. So if I do ZFS get all on tankfs sub, we can see that encryption is on, and the key for this is a passphrase that's being prompted for, but it's actually being prompted for on where we inherited this from. It's being prompted for in tankfs, and it also tells us the last time we told it to start using your encryption key.
So I have a question on the. I think I remember you saying that on the on the sub-file systems that they inherit the keys.
They inherit the wrapping key. The key that the user looks after and manages is inherited. The actual data encryption key is not inherited when you create a sub-file system. It is inherited when you create a clone. And the distinction between those two is a basic ZFS distinction. So tankfs sub here has a completely different data encryption key to tankfs. But the key that the user is looking after to keep their life simple for them, we'd automatically inherited it. I could have forced it to be something different by passing another option to ZFS create if I want to. If I really want to give myself lots of pain and have to type in 20 passwords and it's like, oh, now I need access to the foo part of my documents area, another password. And with that in mind, to help the desktop user that does want to give themselves that pain, we are looking at some enhancements to the GNOME file manager, similar to what we did to integrate ZFS snapshots into it. We've got a design for it. I don't know if we'll actually implement it or not. We do have a PAM module implemented that Glenn and I have been playing with, but we need to work out some more stuff on how to get that right with trusted extensions. So the users they'll just log in with their password, and their login password is also their passphrase, and their encrypted data sets are automatically implemented up. No question?
So last question.
So when you reboot, do you have to just mount these file systems manually?
Yep. So when you reboot, all of the non-encrypted file systems will mount up, and any of them that are encrypted will not be mounted if the keys are not there. If the key is stored on a USB token and that USB token is inserted early enough, it will mount up. But if it's a prompt passphrase that's got to be prompted for, then it's a passphrase that's got to be prompted for, because we don't know what the key is. So any other questions I will take after?
Yeah, we have plenty of time after 5 o'clock. Thank you again.